So what are some consequences? Well, it takes a little bit until mathematics begins to become more than just a problem-solving tool. One of the best examples of this is we've got Pythagoras. Pythagoras, about 500 BC. We all know him for his triangle theorem. Truth is, he should be known for a whole lot more and less than that. He's a cult leader. That's the best way to describe him. He had a cult where he led people towards mathematical religiousness. Like he had people who vowed themselves to him. There were legends crafted about this guy. He walked around wearing white, having a wreath. He had legends about him having a thigh made of gold that he showed off at the Olympics. Like the guy was just like, we're talking like this guy was out there, right? Believed in the magic of numbers. That one I can understand a little bit because there began a culture in Greece where they began to recognize the idea of splitting something in half or in thirds was not only something I could construct and represent easily, but also corresponded to music. Right? If you have a guitar string and you hold your finger down on the halfway mark and you pluck it, you will get a pleasing sound. If you go to the third way, you'll get a pleasing sound. But if you put your finger down randomly and struck it, you will get an unpleasing sound. So there became something about the resonance and the workings of nature that began to reveal themselves through mathematics. It became a way of understanding the world. But he didn't come up with the theorem. There's plenty of evidence that says the Pythagorean theorem was actually discovered way earlier in Iraq. He is just one of the people who helped make it quite popular. So we get the Pythagorean theorem. And we're going to talk about that one because Pythagorean theorem is great. Let's talk a little bit about this. Again, in my class, there are no rules. So I'm not going to give you a formula for us to be using if we cannot understand it at least a little bit ourselves. So we all know the Pythagorean theorem, a squared plus b squared equals c squared. That's excellent. But why? That's the immediate question we should all want to ask. Because if I don't know why it works, there's really no, like a computer could do that instead of me. Like why does this work? It's a beautiful, beautiful story that's totally worth understanding. So let's go into it. It's a super easy proof. So you'll want to sketch this down alongside me. Imagine we have a right triangle. And because I'm going to be wanting to explore the lengths of this triangle, let's give them some labels. Let's call this side A, we'll call this side B, and the other side will be C. Now, if I am playing around with this, I might imagine that this is something like a tile, like a physical tile that I can use to make patterns and art with. So let's make a little bit of art. Let's take this and begin to place it in a little modern art structure. So I'm going to take the exact same triangle and I'm going to repeat it around. So it makes a little bit of like an artistic picture frame, if you will. Right. Exact same triangle, repeated around. So it forms sort of this large square. And I can label some of these sides just to keep track of it. We've got the long side B, the short side's A. So that means this is B and this is A, and this is B and this is A, and this is B and this is A. And on the inside, we've got C. Now to keep track of the fact that this was a physical thing, I'm going to go ahead and give it a little highlighting. I'm going to highlight it a little pink here. And I'm going to highlight these pink as well. And so what we're going to see is we've got some empty space in the middle. We've got some empty space. We've got the triangles, the physical triangles all around the outside, and then some empty space inside that. How much empty space is that? Well, the empty space would have to be a C by C space. In fact, it's a C by C square. So that might be a C square. That would be the size of how big the empty space is in the center. Okay, that's fine. Well, I can take those tiles and I can move them a little bit. So I'm going to sketch out the frame of that large square that we have and just watch as I move the tiles around. So I'm going to start off with still got this tile up here in the top left. I'm going to take the other tile and I'm going to scooch it on up here. So I'm going to take it, I'm going to scooch it on up so that it comes and touches with the next one. So if I scooch it on up, it's going to nest nicely right against it. And then on the other one, I already had a triangle that was sitting right here. And I'm going to take the one that was down here. I'm going to move it on up so it kind of nests right up against it. So I'm going to move it on up so it comes right here. And now I've kind of got everything moved within that frame. Give it a little highlighting so we keep track that these are just the physical tiles. I'm taking them and I'm sliding them around. Now, what we can see happened is that that empty space in the middle has to still be there, but it's just simply not in the middle anymore. It's somewhere else. I can kind of section off those two regions into two different regions, because take a look here. This is the long side, so that would have to be B, and this is the short side that's A, which means that this has to be the remaining difference. That has to be B right there. So the inside that I have here, this is a B by B space. This is a B square. And over here, I've got an A because it's the short side, and B is the long side, which means that A has to be what's left over. So this little space inside here is a by A space. That would make that an A square. So if you take the physical right triangles and you do this with any size, because I didn't give it numbers, what we found is that the empty space represented by A squared and B squared has to always be the same as what was originally represented by C squared. And that's our Pythagorean theorem. Now tell me that's not better than just being handed a formula. Like, oh my golly, like that's just like that's cool. That's like a party. Like you could sketch that on a napkin while you're bored. Like that's just good, right? Like it has to be true. It's not a it works. It's a insight into nature. Like you can't break that if you try. It has to work. So there you go. That's the Pythagorean theorem. Has to work. As we're going to see, it's going to cause a whole bunch of chaos in Greece, a whole lot more than people were expecting.